So, good morning, students. So, this is lecture number 11 of micro engineering subject. So, in this subject, we will discuss about just a minute. Just a minute. Yeah, we'll discuss about the Schottky diode. What exactly mean by Schottky diode? Mm, yeah. So, Schottky diode and its working and its application. So, till that we have completed our 10 lectures. So, if you have missed any lecture or if you want to your doubt is not at all clear, so you can watch through the playlist of the micro engineering, which you have to subscribe my channel first, and then you can go to the playlist and you can watch the entire series of micro engineering subject. Then you can enjoy the lecture of electronic devices and circuit, and you can enjoy the lecture of DTSP. So if you are not subscribed the channel, please go to the subscription. So let's start with the till that in this module we have seen the pin diode. What exactly mean by pin diode? Its construction. We have seen its construction, its working, how it's work, and its application. Okay, this part you have to keep in mind. Means if any device is there, its construction, and they will ask you about construction, and specifically they will ask you about what how it will work. Okay, and then they will ask you about its applications. Some of the application they will ask you. So this is the 5 mark questions. All the questions are all about the 5 mark question. Then in the next lecture we have seen about the gun diode. Gun diode is already over. So what exactly mean by gun diode, what exactly mean by gun effect, we have seen that how electrons are registered by the region, and current cost to be decreasing. Okay, so increasing the resistance after some time. So gun effect is that one. That is the third band we have discussed about. Then its working we have seen, its characteristics also we have discussed. Its applications are also over. Then today's topic of discussion is tunnel diode, and I think Schottky diode. Schottky diode also we will see, and Faractor diode also we will see. Impaired diode. We'll see how much diode we will cover. Okay. So it's about tunnel diode. The tunnel diode is nothing but what? It's basically a very high doped PN junction, near about 10 raised to 19 to 10 raised to 20 per centimeter raised to minus 3. Okay, that is the what you can say, the doping, and it's all about the negatively doped region over here. Let's see in the construction. I don't have a construction of this one. Okay, so what exactly PN junction diode? So uh, 10 raised to 19 to 10 raised to 20 centimeter per cube we are introducing the doping. So what exactly mean by what we are doing in this case? So suppose this is my 1 centimeter for 1 centimeter cube silicon, but we are normally using in the micro GAS GAP indium phosphate, like this one. So this is the cube of, this is the pure semiconductor material. So if pure semiconductor material there, so GS whatever this silicon or germanium, it's not practically be used. It is like insulator at the intrinsic layer. But if you are introducing some kind of impurity in this one, that like boron, indium, gallium, or antimony, arsenic, and phosphorus. So if you are introducing that kind of impurity in this one, so the charge carrier, either holes or electron, that are get introduced in this one, and you are getting the maximum conductivity. Okay, so if my conductivity is maximum, so maximum current cost to be flow, maximum current cost to be flow. So this will happen in this case. So 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 in this case what they are doing, they are doing highly doped region of p injection. They are doing the p injection, and that makes use of quantum mechanical effect called as tunneling. So what exactly mean by quantum mechanical effect, I will tell you. Quantum mechanics effect, I will drop this portion first. Just a minute, I will take pain again. Yeah. So what will happen in this case? So tunnel diode is having a quantum mechanical effect. So normally, till that we know that, suppose this is my nucleus, and this nucleus, it contains a proton and a neutron, and here the electrons are orbit in the specific orbit. Okay, accordingly they are. So so what is going to happen? Electrons are revolving like this one. Okay, like this one electrons are revolving. So suppose if I'm denoting electron like this one. Okay, suppose this is my electron, and suppose this is its axis. Okay, axis is there. So the electrons are there. Some of the electrons are rotating like this one, some are rotating like this one. Electrons are also rotating to their own axis. Keep in mind, electrons are not at all steady. They are just our earth. They are revolving around its orbit, its axis. So some of the electrons are revolving like this one, and some of the electrons, suppose this is the second electrons are there, this is revolving like this one, like this one. Means some of the electrons are like anti-clockwise, some of the electrons are revolving clockwise. So that's why whatever the electrons are there, some of the electrons are that in there, about half of electrons are there, they are anti-clockwise, anti-clockwise, and some of the electrons are there that are clockwise. Okay, so clockwise. So due to which the electron's effect, overall effect, will be get nullified. Means some of the near about half electrons are anti-clockwise and half electrons are revolving clockwise. That's why the effect is nullified. And if what will happen if the more number of electrons are in the clockwise than the anti-clockwise, so if the whatever the material we are observing, that will give you the effect is called as magnetic effect. Magnetic effect. Magnetic effect. So so in this case, the magnetic effect will happen or occur due to what? Some of the electrons are more anti-clockwise than the clockwise. So the property of such materials, the example of such material is nothing but my iron. So iron is the example of this kind of material. Whatever you have heard about quantum mechanics, quantum. So what I exactly mean by quantum effect is nothing but this kind of thing. Some of the electrons are clockwise, some of the electrons are anti-clockwise. So to read and write the memory, SRAM or DRAM, we are using this effect, quantum mechanics we are using. So iron is the best example of this kind of thing, in which you will find more number of electrons are clockwise than the anti-clockwise. So magnetic effect will be occur in this case. Are you getting what I'm trying to say? So quantum mechanics will effect will happen, and due to which what will happen? The tunneling is occur. The tunnel is nothing but a short hole. Suppose this is my mountain. Okay, mountain is there. So we are tunneling from this thing. So we are forming the tunnel, small tunnel from this one. So this tunnel will happen and current cause to flow. Current cause to flow is nothing but the electrons will cause to flow. So this will happen in this case. So this is discovered by the Isaki. Okay, Isaki. So he discovered this effect in 1957, and in the 1973 he got the Nobel Prize for this in the physics. Okay. So if you are adding more number of electrons, or we are doping to the high concentration, then tunnel diode will have a narrow depletion region. So what I exactly mean by narrow depletion region? Near about it is about 10 nanometer. So we know that, suppose this is any material, silicon or germanium or GS. So one layer is caused to be flop. It might be a electron or whole layer, depending on what kind of material we are using. So whatever the electrons are gathering over here due to applying of negative or positive potential over here. So electron, suppose this is my n-type material over here, n-type material over here, and if I am applying a positive potential over here, then the electrons are the majority that are concentrated over here, and they are forming one layer. So this is called as my depletion region. Okay, depletion region. So the length is very small. Depletion layer length, that is nothing but the 10 nanometer. So if my depletion region is very small, then what will happen? If you are applying a small voltage, also small voltage, the current has to be flow. So in the tunnel diode, if you are observing the thing, then at less voltage also current has to be flow. Less voltage is current has to be flow. Yeah. So this is all about happening over here. So in the next slide, I will explain this thing what is happening over here. I will rub this portion. Sorry. Just I will change. Erase all things. So here I will explain with the help of this diagram to you. So if you are observing the thing, this is the VI characteristics of any diode. This is tunnel diode. Then if you are increasing the voltage, the current has to be increasing. So we are getting the linear graph. So linear graph, suppose the line equation is like this one: mx plus c. If you are getting this thing, that is nothing but the if m is constant, y is equal to mx plus c, m is constant, then the whatever the graph is always linear. Keep in mind, the graph is always linear in this case by putting the value of m is my constant. So here up to this point you are getting the linear graph. Okay, that is nothing but we are increasing the voltage, we are increasing the current. So at this point, whatever this point is called as maximum current you are getting. So this current is called as the tunneling current. That is nothing but by ip, that is nothing but my peak current. So peak current is called to flow. So in this case, if you are increasing the voltage, then current cost to be flow. Current cost of at the peak current, after that peak current, the current is cost to be decreasing. Current is cost to be decreasing because in this tunnel diode or in the gun diode, normally in the GS material, gallium arsenide material, so we are having two layers. That is the valence band. I will write as valence band, and in the conduction band. Conduction. So, so what will happen if we are giving the voltage? If you are giving the voltage, and in this GS, you will find the three layers over here. So if you are increasing the voltage across it, though, so some kind of electrons are shifted to this region, conduction band. There some of electrons are, due to which this current is caused to flow up to this point. This current caused to flow. And if you are increasing the voltage beyond the threshold voltage, that is nothing but my VP, the VP voltage, the tunneling voltage itself. So the whatever electrons are there, they will get shifted to the third band. Okay, third band. So if your electrons are shifted to the third band, then what will happen? The electron will not its drift velocity is decreasing. If the drift velocity is decreasing, then its resistance is going to be increasing. If the resistance is increasing, we know that the resistance is increasing, then current also be decreasing. So from that point, the electrons are getting from my conduction band to the third band. That is very what you can say, it is near about this distance, small distance itself. So current cost to be decreasing, so current is cost to be decreasing. And this current, what you can say, this effect is called as negative resistance effect. This effect is negative resistance effect, and where you are getting the minimum current is called as valley point. Minimum current is called as valley point. After that point, the diode is again act as a normal diode. Again, that effect, the diode is act as a your normal PN junction diode. The current cost to be flow. Current cost to be flow. This is all about the tunneling diode. This is all about what? Tunneling diode. So I will explain the concept once again, and then we'll stop over here. Okay. I will rub this portion. So what exactly happening over here? From up to this portion, so it will act as a normal diode, I can say that. This is my valence band, this is my conduction band. So due to this, what will happen? The electron is caused to flow from this valence band to conduction band, valence band to conduction band, valence band to conduction band. But from this point up to this valley point, the electrons in the my conduction band, they are shifted to the third band. And if the electrons are shifted to the third band, then they are getting somewhat sluggish. They are not not conducting the currents. Its diff velocity is going to be decreasing. If the diff velocity is going to be increasing, that is nothing but the increase in the resistance. From this point to this point, the region, whatever this region is having the negative resistance region, and due to which current caused to be decreasing. Current caused to be decreasing. Okay. So, and from this point, value point, again this diode will act as a normal diode. This will diode will act as a normal diode. It will start to the break the junction and the current comes to flow. So today we'll stop over here. So we have discussed about pin junction diode, gun diode, and tunnel diode. In the next lecture, we will start with the Schottky diode, varactor diode. Varactor diode is construction, equal circuit, and impaired diode, trapad, and all that. We will see. So thank you very much for attending this lecture. So see you in the next lecture. So bye bye.